go. All right. Welcome back, everybody. Just a reminder that we're in Chapter 11. We're temporarily skipping Chapter 10. We'll come back to it afterwards, after completing Chapter 7, Chapter 11. That was a weird typo. But yeah, so we'll be coming back to Chapter 10 if we have time. It's going to be close if we have any time at all, honestly. I'm not anticipating it, but that's the main reason I'm doing this out of sequence. And then the coincidental title is Sequences and Summation Notation. We're talking about these sequences and series, ultimately, is what we're working towards, where we have a variable expression, an equation, a formula, whatever you want to call it, and it's just based on a number that you're going to plug in or a previous term. And we called them recursive when you were plugging in a previous term. And we went through lots of examples of just establishing the patterns of sequences, trying to find the patterns in them actually afterwards sometimes as well. That can be very helpful. And we went over some very interesting problems. We talked about factorial notation, which we said we're going to see it over and over and over and over and over moving forward in the calculus sequences. Not too much in Calc 1, but definitely past that. It never goes away. We talked about how we can do things that a calculator can't, certain calculators can't at least, like E, and that's about where we left off. I want to go ahead and point out that Test 3, which will cover Chapter 7 and 11, will be next week, the Wednesday and Thursday, I believe. Yes, the 9th and the 10th. Right? Yes. So we should be finishing this Chapter 11 material next class, or worst case scenario, maybe like 15 minutes of it on the 7th. And then we'll have our test on the 9th and 10th. And then the final exam will be the week after that, the 7th. And the final will be a one-day only. I'm sorry, the 14th. The 14th. I'm looking at the calendar wrong. So that's one day only. I'm only allowed to give one day for the final. I can't do the 2-day thing. Test 3 will flow very much like Test 1 and 2. There will be a review for it. You'll have 2 hours. Same with the final exam, except the final will be cumulative. We'll talk more about that as we get closer to it. But remember, for Test 3, you are allowed a calculator. But you better show your work, because even if you have an answer right, I can go back and take points from you if I feel like you just pulled this, all you did was stuff it in a calculator. You didn't do any real math. That's not something I'd plan on having to do a lot, but I do know that it happens occasionally. All right, so now what we can do is we can continue our journey in 11.1. And we're going to go back to writing terms of a sequence, but now we're going to have that sequence with other interesting aspects of it. Sorry, I was trying to figure out why these slashes look weird. There we go. I guess I had clicked them. All right. So write the first 3 terms of the sequence. A sub n equals -1 raised to the n, then all over n plus 1 in parentheses factorial. Now you might say, well, Mr. Beckner, we know what n factorial is. What's n plus 1 factorial? You just add 1 to the number, that's all. Don't overthink it. You just plug in the number and then see what the factorial turns into. So I remember, in the interest of time, I'm writing less things. All right, so the first term, a sub 1. Just turn the n's into 1s, which you can see I've done in red. -1 to the first power, a negative raised an odd number of times is a negative, so the top is -1. The bottom is 1 plus 1, which is 2, and that's 2 factorial. Now you can't distribute a factorial. You can't say that's 1 factorial plus 1 factorial. It coincidentally is the same answer this time, but it's the only time that ever works. Like if you add 1 plus 2 factorial or 3 plus 5 factorial, that would never, ever, ever work. It's just a mere coincidence for this one example. So 1 plus 1 is 2. Then you do the 2 factorial, which is 2 times 1, which is 2. So you get negative a half. Easy. Now let's do a sub 2, which now we just make the ends 2's. So that's negative 1 squared over 2 plus 1 in parentheses factorial. So again, there is no distribution of factorials. It's like PEMDAS. You have to do the inside first. 2 plus 1 is 3. And a negative raised an even number of times is a positive. So that's positive 1 over 3 factorial, which is 1 over 3 times 2 times 1. 3 times 2 is 6. So that's 1/6. Finally, a sub 3. We're not doing a bunch of these terms. Just trying to establish patterns, see what happens with the alternator and the factorial thrown in there. So now the ends in the original formula become 3's. So that's negative 1 to the third over 3 plus 1 factorial. A negative raised an odd number of times is a negative. 3 plus 1 is 4. So that's negative 1 over 4 factorial. Which is the 4 factorial is 4 times 3 times 2 times 1, which is 12 times 2, which is 24, times 1 is 24. So there we go, our first 3 terms of the sequence. Negative 1/2, comma 1/6, comma negative 1/24. So we see that alternator, the negative 1 at the end, making them go negative, positive, negative. We would expect the next one to be positive, then negative, then positive, then negative, then positive. But we can also see that these numbers, unlike some of the patterns before where they were getting bigger and bigger and bigger, like let's look back at example 1, finding the next terms. 3, 7, 11, 15, they kept getting bigger. B, they kept getting smaller. And you had an exponent in the bottom, so they were getting bigger and bigger in the bottom, which makes the entire number get smaller and smaller. And, you know, that was, they were getting smaller at a decent pace. But compare this exponential bit where the bottom is getting bigger, making the number smaller overall. Compare that to the one we just did. I am so sorry. Compare that to this one where the bottom went 2, 6, 24. The next one, if you put in a 4 here, that would make that a 5 factorial, which is 120. So this next would be 1/120th. So this is getting really, really, really small, really, really, really quick. And I tried to express previously that factorials are one of the quickest growing types of functions. And with a factorial on the bottom, that means it's going to go to 0 because the bottom gets really, really big really quick, which means the whole thing gets really small really quick. So factorials are faster than exponentials. Maybe not initially, but at some point they will pick up speed and just completely overtake them. Motorcycle with high torque versus car with high speed. All right, so now that we've got a good grip on how to find terms of a sequence, whether it's based on the index or the previous terms, and we've introduced some factorial notation and some things like that, let's go into the other half of the namesake of the title, which is summation notation. And I'm going to erase some things up here. First, oops, erase, not pen. Why is that not erasing now? Come on. What's the deal? Why? Just why? Come on, man. Thank you. Wow. Why was that such a pain? What is Word doing to me right now? You can't tell, some of the things it's doing to me because I'm scrolling and then it's not actually scrolling for like 10 or 15 seconds. Okay, so summation notation, we're here. This is used to add several terms of a sequence. This is typical for a series. So a series is this. This is a series. Series uses summation notation, which is this. This thing right here is what we call summation notation. This is the Greek letter sigma. It's a capital sigma, this thing that kind of looks like a weird M, like an M on its side. Now, if you want to be fancy, you give it the extra little divots at the top and bottom, but most people don't do that on the casual. So that's what we call summation notation. That's just the signal, that's the symbol, the signal, that works too, that tells us to get a bunch of terms of a sequence and then add them. That's all it is. You're just going to get a first 3 terms or a first 5 terms or a first 20 terms, and you're going to add them. And you actually don't have to start at the first term. You can start at any term you like. So this is the symbol for a summation. This N at the top represents where we end, and the I equals 1 at the bottom represents where we start. So that was kind of the stuff I was erasing over here, or trying to erase, as you saw, before Word was kicking me in the butt. So this thing over here, it says I equals 1, which is why this is the first term, because this was a 1. This is the first term we're supposed to start on. And then we go to the second term, then we go to the third term, then we go to the fourth term, then we go to the fifth term, then we go to the sixth, seventh, eighth terms, however many terms we have to, until we hit whatever number this is. So this at the top will have to be a number, maybe a 5, maybe a 12, maybe a 17. That tells us where to stop. So that's why this is there. So there's no plus a sub n plus 1 plus a sub n plus 2. You stop at whatever this is. So if this was a 10, this would be a 10, a sub 10. So the number on the bottom tells you where to start. The number on the top tells you where to end. The number on the bottom tells you where to start. The number at the top tells you where to end. And then you're just adding each term. The a sub I, that just tells you what you're going to plug in your numbers into, where you're plugging your 1, your 2, your 3 in. Your a sub i's are going to be things like this. And they don't have to be i's. This could be a sub j or a sub z or a sub n, and then this wouldn't be an n because it would be a number. So just understand that instead of saying a sub n equals this thing and this thing, maybe these are i's now. And that's the only change. It's just a different letter. Doesn't make it any different in concept. This is super simple as long as you wrap your head around the notation. It's literally nothing different than what we were just doing, except now, instead of just listing out the -1/2, the 6th, and the -1/24th, you end up adding them, and then you get a number, and that's it. That's the only difference. We're not doing anything crazy different at this point. We're just going to take the sequence and add them, and that's it. So I make a little memo here, and I said it out loud, but now you can see it in writing. In general, you don't have to start at the first term. You can start at the second term. I can start at the 5th term. I can start at the 20th term. I can start at the 50th or the 500th term, or the 5,001st term, or the 95,001st term. They don't have to be starting at a 1. But you can't start at a term that's bigger than the one you're going to end at. So that's what this says right here. Your ending number has to be bigger than your starting number, or at least equal. You can just have I equals 1 to 1, which you're going to say, well, why did you even write summation notation? And I agree, which is why I would never do that. That was weird. So again, this is going to tell you the function that you're plugging numbers into. This tells you where to start. This tells you where to end. These are just the three things. This right here, these two letters just have to match. You will never see a problem where this is an A sub j and this is an I. All right, so let's pull up our blinders. Find the sum. So this says the sum. When you see this pit right here, I wish I hadn't hit that down. That says sum. Spoiler alerts. Again, this right here says add up some things. And as I already said, I really don't try and make this look perfect every single time. It looks a lot sloppier. It really just looks like an M on its side now. What are the things we're adding? We're adding up I squared. So we're going to be plugging numbers into I squared. What numbers do we plug in? Well, the bottom number tells us where we start, so we'll start with 1, and then we plug in 2, then 3 and 4 and 5 and 6 and 7 and 8 and 9 until we hit the end number, but I said too many numbers intentionally because we're supposed to stop at 4. So we start with the first term, we end with the fourth term. So we need the first, second, third, and fourth terms. That's what this 1 and 4 say. We start with the first, we end with the fourth. So let's find the sequence first. Some people will go ahead straight to just writing out the series with the sequential terms going ahead and being added. I much prefer to do it this way though. Just pretend you don't see that now add. So let's find the sequence first. So A sub 1. Now again, all we're looking at is the I squared. That's all we're using. So what's the I? Well, 1. So 1 squared, 1 times 1 is 1. Easy. That's the first term of the sequence. Nothing new here. It's just the notation. Instead of me saying find the first 4 terms, I gave you a notation that tells you to find the first 4 terms. So A sub 2, now we just make the I a 2. So instead of I squared, it's 2 squared. 2 squared being 4. These are pretty easy to knock out. The third term is just I squared, which again, the I is now 3. Again, the I is like your variable here, 3 squared being 9. And your fourth term just says make the I a 4. 4 squared is 16. So these are the first 4 terms of the sequence. This is all we need to move on. What do? We add them. Add the terms. So the sum of I squared from the first to the fourth terms is the first term plus the second term plus the third term plus the fourth term. If you don't feel like you need to write out this step, that's fine. You don't have to. But I'm being very meticulous to start this. Where we know the first term was 1, we know the second term was 4, we know the third term was 9, and we know the fourth term was 16. 1 and 4 make 5, 5 and 9. Sorry, I thought I had to sneeze for a second. 1 and 4 make 5, 5 and 9 make 14, 14 and 16 make 30. Ooh, you know when you don't sneeze and it burns a little? Oh boy. So there we go. The sum of the first 4 terms of the squared sequence, I squared, is 30. If I wanted to add the first 5 terms, all I would do is change that 4 in the top to a 5. I'd figure out that A sub 5 would be 5 squared, which is 25, and then I'd add another 25 to this, which would be 55. And that's it. Nothing crazy, nothing intense here. No quadrants, no inverse trig functions, no SOHCAHTOA. It's just very basic arithmetic, but with symbols you might not be used to using. So we got to practice it, of course. So for B, let's do the sum. So when I see this sideways looking M, which is the Greek letter sigma, the capital sigma, the lowercase kind of looks like that. That's a lowercase sigma, like a 0 with a hat on it. So sigma, sum. The third through the 7th terms, that's what this says. Start at the third term, end at the 7th term, and you're going to be plugging 3, 4, 5, 6, and 7 into this thing right here. The i's will turn into 3, 4, 5, 6, and 7, and then you just add them up. So we're not going to find the first term. We're not going to find the second term. We're going to start with the third term, which for the sequence I plus 1, that just becomes 3 plus 1, which is 4. And then the fourth term would be 4 plus 1, which is 5. Now, I didn't actually use the previous term. I know that 4 is the same thing as the previous term. You could argue that you could change this into a recursive relationship, and you can, but that's not what we're doing. So when I go to do a sub 5, I don't care that the previous answer was 5. It's just because this little number right here is a 5, I make the I a 5. So 5 plus 1 is 6. And then we need the sixth term, which would be 6 plus 1, which is 7. And then we'll need the seventh term, which is 7 plus 1, which is 8. So there's the third, fourth, fifth, sixth, and seventh terms of this sequence. Now what do? We add them. Why do we add them? Because of the sideways m, the sigma. So we do 4 plus 5 plus 6 plus 7 plus 8. So the sum of the third through seventh terms of the sequence I plus 1. Again, I'm going to write this out even though you might not have to. It just means add up the third, fourth, fifth, sixth, and seventh terms, where each of these a sub 3, a sub 5, a sub 7, etc. is representing the I plus 1s that we already evaluated. The 4 plus the 5 plus the 6 plus the 7 plus the 8. 4 and 5 is 9, 9 and 6 is 15, 22, and then coincidentally 30. Now I did this for a reason, just to see that you can get the same answer for two different series. It doesn't mean these are related to each other at all. They are completely not related to each other. They're not brother and sister, they're not cousins, they don't even know each other. I squared versus I plus 1. First through fourth terms, third through seventh terms. This was 4 terms, this was 5 terms. They don't relate to each other at all. It just happens to be they have the same answer. Crazy coincidence. Crazy coincidence. And there we go. Let's do another. For C, the sum of the first through the 8th term of the sequence 3. And this is the most interesting one. Sorry for that yawn and stretch. Not really a yawn, just a stretch. So this is the series of adding up the sequence where each term is 3. Huh. Well, that looks a little different than the previous two problems. What looks different about it? Look at A. The function, if you will, it doesn't have to be a function, but the thing here, the I squared, had an I in it. And B, I plus 1 has an I in it. 3, you might be thinking I'm just covering something up, but I'm not. That 3 doesn't have an I in it. So what this is no matter what term you are in, the answer is 3. This is known as the constant sequence. If you try to plug in 1, there's nowhere to plug it in, so the answer is 3. If you try to plug in 7, there's nowhere to plug it in, so the answer is 3. If you try to plug in 10 billion, 90 million, whatever, there is nowhere to plug it in, so the answer is 3. If that 3 was a 17, then the answer would always be 17. So every single term of the sequence is 3. We need the first to the 8th term, so a sub 1 is 3, a sub 2 is 3, a sub 3 is 3, a sub 4 is 3, a sub 5 is 3, a sub 6 is 3, a sub 7 is 3, a sub 8 is 3. Deep breath. Obviously, I didn't feel like writing all that down, hence the ... They're all 3. You get a 3, you get a 3, everyone gets a 3. So we're just adding up the first 8 terms, which is a 3, 8 times. So here's the step that, again, most people tend not to write, just showing us adding the first 8 terms, where the A's represent the terms. Each of the terms being 3. Well, 3 plus 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 3 is 24. Now, I actually showed you that, well, since we're adding the same number over and over, some of you might recognize that you can just change that to multiplication of 3 times 8 and you get the same answer. That's not something that most people are generally going to do the rewrite of, but it is true, and it might help one or two of you, so I write it down. All right, let's try another one. So constant sequences are kind of boring, but they do exist. Sometimes no matter what happens, you just get the same output. How about the sum of the first 4 terms? That's what the left bit says. Started the first term, ended the 4th term, of -1 to the I over I. So this has got that alternator, and now we've got an I in the bottom, which when I's are in the bottom, that means that the answers tend to get smaller over time. And that's going to be a really important feature for a lot of series, that the terms actually get smaller as we move on. The last 3 examples, that has not happened. In fact, with C, they were the same each time. With B, they got bigger by 1 each time. With A, they were going to get bigger really quick eventually, 25, 36, 49, 64, etc. All right, but let's go back to where we are. And let's see what happens here. -1 to the I over I. So we need the first 4 terms. So the first term, just make the I's 1s. I went back to using red here. -1 raised an odd number of times is a negative. And 1 in the bottom is just 1. -1 divided by 1 is -1. So there's our first term. The second term is -1 squared over 2. A negative an even number of times is a positive. So that's +1 in the top over 2, which is a half. Don't even need to simplify it. A sub 3 is going to be -1 to the 3rd over 3. -1 cubed is -1 because that's an odd number of times. And then 3 in the bottom is just 3. So -1/3. A sub 4 is -1 to the 4th over 4. A negative an even number of times is a positive. So it's +1 in the top over 4. So these answers are getting smaller in absolute. Notice I had to say in absolute because we're kind of going negative, positive, as we expected because of the alternator. So the next one would be negative, then positive, then negative, then positive. And that trend would continue forever. And then the outputs, if you ignore the signs, are getting smaller each time. But because they're bouncing between positive and negative, it gets bigger going from A1 to A2 when I don't say absolutely, because a half is bigger than -1. Then it gets smaller to -1/3. Then it gets bigger to 1/4. Then it would get smaller to -1/5, and then bigger to +1/6. That's why I prefer to say that they're getting smaller in absolute. If you disregard the signs, they are getting smaller each time, because that's an important issue moving forward. All right, so we can say that the sum of the first 4 terms, first term plus second term plus third term plus 4th term, is the sum of those answers, -1 plus a half plus -1/3 plus 1/4. And here's where you get annoyed at me, but Mr. Beckner, these are fractions. I don't want to add fractions. Too bad. Sometimes we got to add and subtract and multiply and divide fractions. Just facts of life. All right, so between denominators of 1, 2, 3, and 4, I know I didn't write the 1, but it's implied to be a 1, your LCD would be 12. So then you just make all those denominators 24s, and you divide and multiply to get your new numerators, and you should get these values. So for the first one, 1 will go into 12 12 times. 12 times 1 is 12. So -1 is the same thing as -12 over 12. For the 1/2, 2 will go into 12 6 times. 6 times 1 is 6. So that's +6 over 12. For the third one, 3 goes into 12 4 times. 4 times -1 is -4. And for the last one, 4 goes into 12 3 times. 3 times 1 is 3. Again, We have been doing LCDs all semester long. If you can't handle that, I'm terrified. I really hope we can all handle that by now. So then we just add and subtract the tops. Negative 12 plus 6 is negative 6. Minus 4 is negative 10. Negative 10 plus 3 is negative 7. So negative 7/12. That is a really loud bird. Sorry, I'm distracted. I'm kind of curious if you can hear it, but there's a bird screaming outside. All my windows are closed, but all right, ADD. So the sum of the first four terms of this isn't even 1, it isn't even -1, it's a fraction. And if you kept going on, this number might continue to get smaller in absolute. Maybe it gets a little bigger, but it probably isn't going to move very far, because the next sequence is going to be -1/5 and +1/6 and -1/7 and +1/8. We keep adding or subtracting smaller and smaller and smaller numbers. So most of the effect of this series is found in the beginning, of where you're going to be close to the actual answer if you add 50 or 70 or 90 terms. So the sum of the first four terms being -7/12 isn't going to be too far off than, say, the sum of the first 10 terms. It might be like 1 off, but that's, it's not like 30 or 40 or 50 off like the I² sequence. Next you'll add 36, then you add 49, then you add 64, then 81, then 100. What I'm trying to introduce you to is the concept of what we call a convergent series, where these things, if you just keep adding over and over and over and over and over and over and over infinitely many times, that you can actually get a finite answer sometimes. All right, but before we establish that, let's do one last type of example, and then we'll move on to the next section, which starts addressing kind of the things I was talking about there. Actually, that's the third section. Write the given sum in summation notation. So in other words, write it as a series. So what we're doing here is, instead of starting here and ending with this before we added everything, so instead of starting here and ending here, we're going to flip the script. We're going to be looking at the pattern of numbers, and we're going to try and establish a formula for the term and write the sequence going from the first to fourth term or the second to the millionth term, something like that. We're just flip-flopping the order of these two things, these two events. All right. So I'm trying to not show the little arrows. So for A, I didn't just give you an answer. Just giving you a number makes it impossible. I can't just give you a number and say, find the series. Even the most brilliant mathematicians can't do that, because there are literally infinitely many answers. So we have to give you something broken down into sums so that you can see all of the little individual terms. So 1², 2², 3², 4², 5², 6², 7², 8², 9², 10², 11², 12², and 13², all being added. That's what this series represents. So the 1² is maybe the first term, the 2² is maybe the second term, the 3² is maybe the third term. As I said, maybe, because we don't have to start at the first term, but we usually like to start at the first term, unless it's just blatant that we want to start with the 17th term or the 25th term or something weird. Like if we started with a 25², then a 26², then a 27², I would probably just start with the 25th term then. So here are the things we need to do. We need to figure out the formula for each of these individual terms. We need to find out what term we're starting with and what term we're ending with. Well, 1², 2², 3², 4², 5², blah, 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 13². It seems like the exponent isn't changing. All the exponents are 2's. So I think that this is going to be something squared. The A sub n is going to be something squared. It's going to be something squared. But the question is, what is the something being squared? Well, oops. The first term has a 1 being squared. The last term has a 13 being squared. So to me, that says it's probably a good idea to start with the first term being number 1 and the 13th term being number 13. So we're going to go from the first to the 13th term. So the I will start with a 1, and then the top would be the 13. Now all these terms are just squaring whatever number we are in the sequence. So they're just all being squared. So that gives us this. We're going from the first term to the 13th term, the first term to the 13th term, and we're adding. Because these were pluses, that's why we have the sigma, and the 1 and the 13. And then the formula for each of those things is just the term in the sequence, which we call I, and squaring it. So each of these a sub n's will be n squared, or if you prefer, a sub I is I squared. It doesn't matter what letter you use as long as you're consistent. If I want to write a sub j, it would be j squared. If I want to write a sub z, it would be z squared. There we go. I've got an alternate version for this. I don't have to give you it written this way, 1 squared, 2 squared, 3 squared, blah, 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 13 squared. I'm saying here, I could give you this as the problem instead. I'm not saying that you changed it, I'm saying I give you this. This is a little tougher. 1, 4, 9, 16, 25. This you have to have a much deeper pattern recognition understanding ability. You have to recognize now that these are squared numbers, 1, 4, 9, 16, 25. It might be a good idea for you to know your cube numbers, 1, 8, 27, 27, 64, 125, et cetera, et cetera. But everyone should know their squared numbers. We've seen these 10 billion times in math classes. So you have to recognize that that's 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, all the way up to 13 squared, and then you can get your answer that way. So sometimes you're given it in an easier format with things not expanded. Sometimes you're given them after the math's already been done a little bit, and you have to try and predict, well, what happened? How did we get to this 9? How did we get to this 16? How did we get to this 25? There's actually a third way you can figure this one out. You can say, oh, well, each time we're adding 3, then we're adding 5, then we're adding 7, then we're adding 9, then we're adding 11, then we're adding 13. The addition increases by 2 each time. Now, is that going to be helpful for establishing the pattern? It would just look very different. It would be recursive instead, but you would still have a pattern. So maybe then you just have a recursive relationship instead. But I don't want to do it that way because it's more confusing. All right, B. So an actual new example, just 1 plus 2 plus 3 plus 4 plus da 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 52. 52 is a pretty common number you see in math because it deals with cards. There's 52 cards in a standard deck, 13 of each suit, and then you get into all sorts of crazy probability theory. If you want to go into gambling, learn your probability. So how can we establish a pattern for this and put it into a sigma with a starting number and ending number, and then just a little basic formula for each term? Well, the first term we see as a 1, so that's a good idea. Sorry, that's a good, excuse me, now I got the hiccups. I'm all over the place today. Coughing and almost sneezing and hiccuping. All right, so this first number we see is a 1, so that, I don't know, that just makes me really want to start at the first term. The last one's a 52, and each thing seems to be incrementing by 1. So why not just call each term of the sequence the number from the sequence? Why don't we just call each term I? We're starting with 1, we're ending at 52, and then we can just go, boom. The sequence is I. I will tell us the answer, and that's just based on whatever term we're in. So we go from I equals 1 to 52 of the sequence I. There are literally a billion, trillion, quintillion answers to this. Here's an alternate form of that. Let me scroll up so you can't see that. Here's an alternate answer. You could start at the 0th term, which we don't really do in pre-calc 2, but you do in calculus. And then we could go to the 51st term, and then we can have the sequence be I minus 1. That would be the exact same thing. And if you don't, I'm sorry, I minus 1, I plus 1, excuse me. Why I said minus. If you plug in 0, 0 plus 1 is 1, so the first term is 1. If you plug in 1, 1 plus 1 is 2, so the second term in that sequence will be 2. If you plug in 51, 51 plus 1 is 52. So you would get the exact same 52 terms. It's just we have what we call an index shift, and it changes the formula slightly. Or you could go from I equals 2 to 53, and you could do I minus 1. That's why I had the I minus 1, because I was going to show you a third variation. Same exact thing. If you listed all 52 terms, you would get 1 through 52, and then you'd add them. Because when you plug in 2, 2 minus 1 is 1. When you plug in 53, 53 minus 1 is 52. Now in my math lab, they'll probably tell you what term to start with if you have this type of problem. So that way, they don't have to account for the fact that there's a billion answers. Just makes it a little easier for them. All right, C. Getting into a little crazier. Where's my other one? Go. There we go. 7 plus 7 squared over 2, plus 7 cubed over 3, plus 7 to the 4th over 4, plus 7 to the 5th over 5, plus 7 to the 6th over 6. You get the idea until you get to 7 to the 9th over 9. Now again, I don't have to give you the 7 squared. I could have written that as 49. I don't have to give you the 7 cubed. I could have given that to you as, what is that, 721? Why did I say 721? 343. 721. Doesn't matter. Et cetera, et cetera. And then that would make it much more complicated to figure out the pattern at the top. We would hope that the 7 and then the 49 would give you a strong inclination that it's 7 squared, 7 cubed, 7 to the 4th, 7 to the 5th, et cetera. The bottom numbers are pretty easy to figure out. Now, I didn't write a bottom number here for the 7, but it could just be 7 over 1 to make it a little more obvious. So there's two components of the formula we have to have. We have to have something for the top being a 7 raised to a power, and we have to have something in the bottom to represent the 2, 3, 4, 5. Now the 7's not changing each time, so it's going to be 7 to a power. And the power is matching the bottom, so why don't we just make that the index? This is a 7 over 1 with an exponent of 1, and then we can start at 1. So we'll say that that first one is the first term. This is the 9th term. And again, here's just the rewritten version of the first term in red over here, right here. That you could say that's 7 to the, what the heck just happened? 7 to the 1st over 1. That's a rewritten form of the first term. So with that being the first term, that being the last term, it seems like each term has got a 7 raised to a power. We'll call the power the term we're at. And the denominator would also be the term we're at. So the exponent in the bottom we're going to call i's. That base has to be a 7. So each term, this a sub I, darn it, has to be 7 to the I over I. So that's each term. So we want to write our series going from the 1st to the 9th term. We get this. We start at the first term, we end at the 9th term. And then each term is 7 to the I over I. And if you don't trust this, plug in some of these and see if they match. Plug in 1, that's 7 to the 1st over 1, good. Plug in 3, 7 to the 3rd over 3, good. Plug in 9, 7 to the 9th over 9, good. I didn't ask you to add these up, I just said to rewrite the series using this different notation. This different but important notation. That again, in Calc 1, you really won't see, but in Calc 2, you spend at least 2 chapters dealing with this stuff. Maybe 1, depending on the book. But it should be 2, in my opinion. And then when you go on to the differential equations after that, you see it in them. You go on to Calc 3, you'll see it in there. It doesn't go away. And I think that's it for the section. It is, good. So we've got the basic concept of how to find terms of a sequence. We've got the basic concept of what it means to be a series, and we'll have to practice so that we remember how to use the notation. We practiced going from series notation to expanding and adding. And we've also gone from having something expanded to writing it as a series to take up less room. See, the series is awesome because it takes up way less room. Imagine that we had 5,000 million of these things, also known as 5 billion. You wouldn't want to write out 5 billion terms being added. You want to write the sum from 1 to the 5 billionth term of, and then just write one single term with a formula. It's so much more condensed. So over the next two sections, we're going to study two types of series. We're going to study the arithmetic series, and we're going to study the geometric series. Now, the names are not good, in my opinion, because you think, oh, arithmetic means add, subtract, multiply, and divide the terms, and then geometric means you're dealing with rectangles and triangles and what? Huh? No, actually, they're terrible names, just like a lot of things in math are terribly named. An arithmetic sequence means that the next term is the previous term with a number being added to it. A geometric sequence means the next term is the last term with a number multiplying it. Why don't they just call it the recursive addition sequence series and the recursive multiplicative series, which would be more aptly named. But either way, only studying one at a time. 11.2, the arithmetic sequence. An arithmetic sequence is one in which each term after the first is a constant difference from the previous. This constant difference we tend to call a common difference, and it tends to be denoted with the letter D. Does it have to be the letter D? No. In difference, you might think, oh, so we're subtracting these. There's a subtraction to get the D. You take the next term minus the previous term, but all we're saying here is you just keep adding the same thing over and over and over. You just take the previous term and add 10, or take the previous term and add 5. So how do you get to the 7th term? You add 5. How do you get to the 90th term? You add 5. How do you get to the billionth term? Add 5. Add 5 to what? The previous term. So an arithmetic sequence is recursive. So this common difference is just the number that you keep adding up over and over and over. So that's why I said the old term plus a common difference gives you your new term. For this example here, which you couldn't see. Let's get our blinders. There we go. So I shouldn't have had that up there yet, but it is just at least a good example of saying, all right, your new term is the old term plus 11, or your new term is the old term plus 5, or your new term is the old term minus 12. It can be minus as well. They can go down, they can go up. In fact, I'm going to add a word to this. New term equals old term. So example 1, find the first 5 terms of the arithmetic sequence whose first term is 3. See, this is recursive, so we have to give you the first term. And the nth term is the n minus 1th term plus 11. In other words, the new term is the old term plus 11. That's what that says. And the thing that you're just going to keep adding over and over is what we call the common difference D. I'm going to give you a minute to write because I know some of you are probably still catching up. All right. So I had to tell you that the first term was 3. I could have told you it was 5. I could have told you it was negative 7 million. Could have told you it was 0. But I have to tell you a first term. If I don't tell you the first term, you can't do anything. So the first term is 3. The second term is the previous term plus 11. So it's the first term plus 11. The first term being 3. So we do 3 plus 11, which is 14. And that's it. Doesn't really feel like we've done anything different because we haven't. We did this exact type of problem last time. We just didn't give the name arithmetic sequence, and that the number being added is known as a common difference. All right, so how about a sub 3? Well, that means we're going to take the second term and add 11. So it's always n minus 1, so 3, 2, 5, 5 and 4, or 1,000,000 and versus 999,999. The second term we just found was 14, so it's 14 plus 11, which is 25. So we went from 3 to 14 to 25. You could just keep adding 11. You might feel like you don't have to show your work, and that's okay. But I'm going to, of course, show my work. So the fourth term is the third term plus 11. Third term being the 25, and 25 plus 11 is 36. We said to find the first 5 terms. So the fifth term, the first term was given to us. If I said find the next 5 terms, we'd need the sixth term too, so pay attention to the language. Well, that would be the fourth term plus 11, the fourth term being the 36, and 36 and 11 make 47. Now, I didn't say to add these. You might be told to add them. You might be given this written as a sequence, as a series. So pay attention to the instructions. There we go. In general, let me do this. Let me scroll down. Let's erase this, and then I'll undo that erasing. In general, if the first term is known for an arithmetic sequence, if we're an arithmetic sequence, if we know that the first term, the second term, the third term, the fourth term are all just adding 7 to get to the next one, or adding 11, like in the example, to get to the next one, you don't need the middleman. Think about it this way. How could you go from 3 to 47 without finding the second term, the third term, the fourth term? How could you go straight from 3 to 47? You know you're just adding 11 over and over. It's just a matter of how many times you're adding 11. Well, we're starting at the first term, so we got to go second, third, fourth, fifth. That means we're going 4 more terms down the line. So we got to add 44, 4 times 11. Because 11 to get this one, 11 to get this one, 11 to get this one, 11 to get this one. That's 4 11s, which is 44. So if I wanted to get to the 10th term, I would just be adding 5 more 11s. So I'd be adding 99. Now, what people accidentally do sometimes is they'll say, if I want the 10th term, I need to do 10 times 11, and that's what I add. But not quite. Because the first term, you don't add 11 to get to. So that's why if you want to get to the 10th term, you're only going to add that 11 9 times. If you want to get to the 5th term, you're going to add that 11 4 times. If you want to get to the, say, the 100th term, you're going to add that 11 99 times. So that's what this formula says. You take the starting number. This n minus 1 is 1 less than the number of terms you want to find. So if you're trying to find the 100th term, that would make this 99, and then you just multiply it by the d. Sorry. What? There we go. So the things I was saying a minute ago is written in red right here. Your last term that you need, the nth term, whatever term it is you need, is just the first one plus, and then you're adding that common difference over and over and over, but it's always going to be 1 less time than whatever you're trying to find in terms of a term. So if you want the 7th term, you're going to be adding 6 of these. Adding the same thing over and over and over just means multiply. And this n minus 1 represents 1 less than n. This is not some kooky, crazy formula, but it is an important formula. It says to find whatever term, you start with the first term, and then you add that d over and over and over, and it's just 1 less time. But instead of literally adding 11, 11, 11, 11, 11, 11, 11, just take 11 times 6, or 11 times 10, or 11 times 99. So if I don't want the middleman, all I want is the start and the end, this is going to be helpful as long as it's arithmetic. Now, you have to be told it's arithmetic, or they have to establish a pattern that it's arithmetic to use it. So just going back to example 1, the first term was 3, that common difference was 11. The common difference always being the number added or subtracted if it's recursive. So if that was a minus 11, then the d would be negative 11. So the 5th term we can just say is the 4th term plus 4 times that d. 5 minus 1 times the d, because we're going to add it 4 more times. So that's 3 plus 4 times 11, which is 3 plus 44, which is the same 47. It works. Definitely works. We're not just making up nonsense as we go. We got about 18 minutes, 16 minutes. Okay. So let's find the requested term without doing the middlemen. Now, on a homework or a test, you could certainly still find a sub 2, a sub 3, a sub 4, a sub 5, a sub 6, a sub 7, 8, 9, 10, and then get to 11. But what if I asked you for the 5 millionth term? Do you really want to do that middleman approach? No, you don't, because you'll never finish the job. So that's what this is really for. If you wanted some extravagantly large nth term, and by large I mean in terms of, you know, it's the 5 millionth term or the 5,000th term or even the 500th term. Heck, I'd do it for the 50th term. So by giving you the, the first term in the D, that is me telling you this is an arithmetic sequence. That was weird. So that's me telling you it's arithmetic, where each time the next term is 8 less than the previous one. So this one's actually going down. We're going to start at 40, and then it's going to be smaller and smaller and smaller. And we want the 11th term. So that means we're going to be subtracting 8 over and over. If we want the 11th term, that means we're going to have to subtract 8 10 times. So I could just do 40 minus 8 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 minus 8. I do believe I counted that correctly. Pain in the butt to do, though. So we go, no, why don't we just multiply 10 times the negative 8? So that's what we do here. So we take the first term, we say the 11th term is the first term plus. Since we want the 11th term, we have to subtract 1 from 11 because we won't add or subtract that number 11 times. We would add or subtract it 10 times, then times that constant difference. 11 minus 1 being 10. So that's 40 plus 10 times negative 8, which is 40 minus 80, which is negative 40. Again, some student might struggle with this and say, all right, it's going to go 40, then 32, then 24, then 16, then 8, then 0, negative 8, negative 16, negative 24, negative 32, then negative 40. And that would be fine if there's only 10 or 11 terms, but if I ask for the 100th term, you're going to hate life if you're doing it that way. So this is a shortcut to go from first to last. Obviously, I'm pointing at a 2 for a reason, but let's ignore it for a hot second. What if I told you, and by the way, A, if you didn't catch that, I made example 2A, just the previous example, just establishing that this does actually work. For C, I'm telling you the first term is 1. Then instead of giving you the common difference, I give you the recursive relationship, which means you need to know how to extract it. And if you don't know, then what you can do is just find the second, third, fourth terms, and then find the pattern, which the pattern would be very easy to see. But with a recursive relationship, if they're just adding or subtracting a number, that is the common difference D. So that just says each term is going to take the last one and add 2. Now I want the 103rd term. I definitely don't want to have to find the 7th term and the 20th term and the 58th term and the 91st term and the 100th and 101st and 102nd term to find the 103rd term. Time consuming, pain in the butt. Let's go from first to last. So that common difference is the 2. And again, if you don't trust me, do a sub 2 would be a sub 1 plus 2. So that would be 1 plus 2, which is 3. Then the third term would be 3 plus 2, which is 5. Then it would be 5 plus 2, which is 7. And you would see that you just keep adding 2 to the previous term. So the 103rd term, to go from the first to the 103rd term, we have to add that D 102 times. So we start with the first term, then we add that D 102 times, which just gets rewritten to look like this. Again, that's just plugging the numbers into the formula, but I don't even like memorizing the formula, honestly. I like using it as a concept. Take the first term and add that D one less time. Scout's honor, I never memorized this formula. I memorized the concept. I love concepts, but you should know that about me being your trig teacher by now. All right, 103 minus 1 is 102, so that's 1 plus 102 times 2, which is 1 plus 204, which is 205. Didn't need the middleman, middle woman, whatever, middle person. So I can give you these arithmetic sequences in multiple ways. I can give you the first term and the common difference. I can give you the first term and the recursive relationship between them. I could actually just give you, lay out the numbers 1, 3, 5, 7, 9, and then you can establish the recursive relationship. All right. And that's what I'm trying to say in the screening. So this was us figuring it out. All right, the first term was 1 plus 2 is 3. And I said this earlier. It's just me that this is me writing it down. The second term, 3 plus 2 is 5. 5 plus 2 is 7. And then you can just subtract any of these terms. You can subtract the third and the second. 5 minus 3 is 2. You can subtract the fourth and the third. 7 minus 5 is 2. You could subtract the fifth term and the fourth term. 9 minus 7 would be 2. 11 minus 9 would be 2. So that's another way of establishing the common difference, 1, 3, 5, 7. Clearly, we're just going up 2 each time. All right, let's move on. The sum of the first n terms of an arithmetic sequence is. How much time do I have? I really want to show the proof of this formula. But at the same time, I don't think we have time for it. But I'll give you an argument as to why it works. The sum of the first n terms of an arithmetic sequence is, so S sub n, now this could also be rewritten in sigma notation, so you could go that sideways m letter, and then from 1 to n. So again, this is just another way of writing it. You're going to see some writing to the right, that's okay. Oops, why did I write n? Why is it, it threw me off because it was in 2 colors. That's why I did that. From I equal 1 to n. This is what that means. The sum of the first n terms. You have to start at the first term. You can't start at the third term and go to the 7th term. You have to start at the first and end at the 7th, or start at the first and end at the 10th, whatever. But this is only for arithmetic. So this S letter, we don't use this if it's not arithmetic. So if you can't prove or you're not told that it's arithmetic, then you can't use this formula. So this says n over 2 times the sum of the first and last term. N over 2 times the sum of the first and last terms. So in black ink, what I have here is the number of terms, which is the n. N is the number of terms of the sequence. So that's what that is. And then the rest of it is the average of the first and last term. So this right here, if you delete the n, that just says a1 plus an over 2. That's adding 2 things and dividing by 2. That's an average. So that's what that is. It's the number of terms times the average of the first and the last term. What you can essentially do, and the proof takes more than 10 minutes, which we only have 10 minutes, that's why I'm not going to show you the formal proof, but this is how it flows. Because you just keep adding the same number over and over and over and over and over, that means that you can just take the weight from the last half of the numbers and give it to the first half of the numbers, and you can actually just make them all the same. You can average them. So if your first term is 2 and your last term is 10, that says the average of all the terms would be 10 plus 2 divided by 2, which would be 12 divided by 2, which is 6. So if your first term is 2 and your last term is 10, that means the average term is 6. So maybe the terms go 2, 3, 4, 5, 6, 7, 8, 9, 10. You can take 4 from 10 and give it to another number. You can take 3 from the 9 and give it to another number, and there you go. I think I went from 2 to 10, and then I changed it. Yeah, I did. Hold on. Let me actually write those numbers down. Let me write something down for you. If I said a sub 1, this is a different problem, is 2 and a sub n is 12, that says that the average term would be 2, I said 10 before, sorry, 2 plus 10 over 2, which is 12 over 2, which is 6. Now, I didn't say how many terms there actually were, but let's just say they were going in increments of 1. So it goes 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the sequence. It's the sequence with a common difference of 1. What I can do is I can take some numbers from over here, anything bigger than 6, and give them to over here. So we have an extra 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 that I can give over here. So I can give 4 of them to the 2 to make that a 6. I can give 3 of them to the 3 to make that a 6. I can give 2 of them to the 4 to make that a 6. You get the idea. So it's just you're taking 4 from the 10 and you're giving 4 to the 2 to make that a 6. You're taking 3 from the 9 and you're giving 3 to the 3 to make that a 6. You're taking 2 from the 8 and giving them to the 4. You're taking 1 from the 7 and giving it to the 5. And that just makes the new sequence 6, 6, 6, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, that's right. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's just reorganizing the numbers, and you don't even have to think about any of the middle ones because they're going to continue to average out. The 3 and the 9 average out, the 4 and the whatever average out. You just keep doing that. It's just reshifting the numbers, which is why you can average them and then just say, all right, we'll multiply by the number of terms. Because the average term will be 6. If you have 9 terms, you add 6 9 times. So it's a really fascinating concept. The proof, like I said, takes way more than the 4 minutes to explain the basic concept. Feel free to check it out. It might be in your textbook, but I don't have my textbook in front of me today. But it's definitely on the internet. All right, so it's just a reorganization of numbers. So what can you do? You can either A, memorize the formula, which is the green ink, or you can B, memorize the concept that for an arithmetic sequence, because of the balancing of the numbers, you can just take however many terms you're going to be adding and multiply it by the average of the first and last term. This is how I learned it, the black version, but many students like memorization of formulas, so you'll get the green version. With our 4 minutes left, 5 minutes left, and this was to use prove be told, it's a sequence, that the sequence is arithmetic. Oh, and I didn't show you this part either. This was just me rearranging the n and the 2 to actually put the average part there. But with our last few minutes, let's try out one of these. Cover your eyes, avert thine eyes. All right, find the sum of the first 25 terms of 5i minus 9. Now again, this only works if you start at the first term. You can do an index shift, which is a common thing you learn in Calc 2, something I kind of established earlier where I showed one series starting at 0, one starting at 1, one starting at 2, and they all meant the same thing. So if this started at 2 and ended at 26, I could shift it to 1 and 25, but we're not doing that in this course. So I told you to find the sum, and you go, all right, well, that means I got to find the first one, the second one, the third one, the fourth one, all the way to the 25th, and then I got to add those 25 things. That's one version. And it's not the end of the world since it's only 25 terms, but what if I said 250 terms? What if I said 2,500 terms? You're going to hate me. And you go, well, no, hold on. Mr. Beckner said if I can prove this is an arithmetic sequence, if I can prove that each term, each next term is just the last one plus or minus of the same number over and over and over, I got a simple formula. Just take the number of terms times the average of the first and last term. So let's show it's an arithmetic sequence by finding at least 2 or 3 terms, sorry, at least 3 or 4 terms, and establishing the common difference. So what's the first term? The first term is going to be 5 times 1 minus 9. Oh, geez, I've got too much shown up here. Let's scroll down, move this over here, this down, there we go. All right, so the first term is 5 times 1 minus 9, which is 5 minus 9, which is negative 4. I'm going kind of quickly because we're short on time. The second term would be 5 times 2 minus 9. See, this right here is not recursive. We're just plugging in an I, not an A sub in minus 1 or I minus 1. So the second one is 5 times 2 minus 9, which is 10 minus 9, which is 1. Now going from -4 to 1, we've added 5. The D between these two is 5. Now that doesn't prove anything. We have to show that that's consistent, so we need to go to at least the third term. Some people suggest to go to the fourth one, but I'm going to stop at the third. So the third term, the third term would be 5 times 3 minus 9, which is 15 minus 9, which is 6. And going between 1 and 6, that is another difference of 5. I did show the work for A sub 4 in actuality. A sub 4 would be 20 minus 9, which is 11. And going from 6 to 11 is also a common difference of 5. So again, we established it by the third term, but we really established it by the fourth term. So we can see that the common difference going from first to second or to third or fourth or to fifth term is always going up 5 more. Our first term was -4, which we proved up here. We need to find the sum of the first 25 terms, so the n is 25. So the main question we need is, what is the 25th term? Because we've got to average the first and last. So you might be thinking, oh, well, just find all of them. No, you can go straight to the last one because this is the formula based on I. It's not even recursive. So just plug in 25 here. So A sub 25 would be 5 times 25 minus 9, or over here, which is 125 minus 9, which is 116. So there's our 25th term. So we have our first term, which was the -4. We have the last term, which is the 116. We know we're adding up 25 terms. So either apply the formula or the concept. I like the concept, take the number of terms times the average of the first and last. Also, this purple link just shows it as a recursive relationship using this formula above, that the whatever term you want is the first one plus one less of the D's. So you can see the first one was the -4. If we have 25 terms, that means we take 24 times the D. 24 times 5 being 120, minus 4 is 116. It still works. All right, so the sum of the first 25 terms of this sequence. Also, if you wrote it this way, it's the same thing. These two mean the same thing, but we can only write S sub 25 once we know it's arithmetic, which we've shown. But I'm not going to find all 25 terms. We're just going to take the number of terms 25 times the average of the first and last. -4 plus 116 over 2, which is 112 over 2. And if you do that math, you're going to get 1400. Half of 112 is what, 56? And then 56 times 25 is 1400. That might have seemed like a decent amount of work, but it's less work than finding 25 terms and then having to add them. That's a lot of bookkeeping. And again, the A sub 4 didn't really have to do. The purple was just establishing results in a different way. This is a very powerful technique. Are all sequences and series arithmetic? Absolutely not. Will we see enough of them in our course to need to memorize this and understand this? Absolutely. So we're going to call it a day there. We'll do some more of this stuff next time. We might actually finish everything next class, but that'll be tough. I don't anticipate that. I'll adjust anything if we have to, but that 11.3 just might spill over a teeny bit into the Monday. I'm going to do my best to finish 11.2 and 11.3 next class though. So yeah, remember the test dates. We already talked about those. Work on your homework. We did finish 11.1 today, so that's due in a week, but not 11.2. If you have any questions, email me. Besides that, we'll see you on Wednesday. Not a lot of time left in this course. Only 4 more days, 4 more classes. And that's it. Take care.